All right, everyone. Welcome to the afternoon session. Welcome back from lunch. This is the session on SE for AI, and our first speaker is Chengcheng. Chengcheng, take it away. Oh, just give us a second.
Yeah.
Wonderful. Go ahead.
Hi, everyone. I'm Chengcheng. Thanks for listening to my presentation. Today, I will present my work, Runtime Prevention of Software Integration Failures of Machine Learning APIs. We have released our benchmark and code through this link. So let's first go to the introduction. Machine learning cloud APIs offer effective solutions for a spectrum of cognitive tasks. They enable developers to easily incorporate learning solutions into software systems. It requires less domain knowledge and completely removes developers' burden of designing and training neural networks. Due to this convenience, many software applications in a variety of domains are incorporating machine learning APIs. Unfortunately, these applications often experience integration failures in their use of these APIs. It's a type of failure that occurs when the output of an API invocation is incompatible with the software component that uses this output. Integration failures are widespread in applications that use these ML APIs due to underspecified interfaces of the latter. This phenomenon is particularly visible in two ways. First, every cognitive task performed by an ML API typically has more than one correct answer. Second, the model used by an ML API is inherently probabilistic, whose outputs are only statistically reliable over many input samples. To better understand these integration challenges and their consequences, just consider these applications, which is called flood depth. It's an open source application that uses vehicles as a reference to estimate the flood depth. As shown in the code, it first identifies objects in a street view image uses the ML API. It then iterates through all the identified objects and finds the one whose name matches one of the vehicle-related keywords in the target list. Finally, it invokes and predicts flood depth upon these objects. This code snippet is straightforward on its own, but the software and the ML does not work well when integrated together. Here shows the API outputs onto adjacent frames in the video. As we can see, the left car is successfully identified by the API in both frames and is labeled as vehicle. However, without a clear API specification, the software developers do not anticipate the vehicle output and do not include it in the target list. As a result, this correct but unexpected output, this car will be mistakenly skipped in the flood depth prediction. Furthermore, the van in the middle is correctly identified in frame 1, but gets missed in the almost identical frame 2. Again, lacking API specification, the software do not anticipate this incorrect output and would omit this van in the flood depth prediction. With these vehicles mistakenly skipped, the software underestimates or even completely fails to predict the depths. Similar problems occur widely in software applications that use ML APIs. The straightforward way of integrating machine learning APIs, like that in example, cannot tolerate the API results that are out of context or occasionally incorrect, which leads to software misbehavior. It is desirable to have an adapter that converts ML API output at runtime to better fit the software component that uses the output, compensating for the underspecified interfaces of the ML APIs and reducing integration failures. To design such an adapter, there are several challenges. First, how to judge whether an ML API output matches the expectation of the software. Lacking the API specification, software developers do not know what output they may get from the API invocation and do not have a standard way to specify what output they expect. How to automatically extract that expectation and hence judge whether an API output matches the expectation of software is an open question. Second, how to judge whether an ML API output is correct. Like an ML API specification, it is difficult to know which specific output of an ML API invocation would be wrong. In fact, judging the correctness of an ML API that emulates human cognition tasks typically requires human effort, which is difficult to carry out during the runtime detection. And third, how to conduct compatibility checking and conversion with low overhead. High overhead is not acceptable for software users. Consequently, we cannot use expensive techniques such as retraining and updating the neural network models at runtime, which will typically take hours of time. Next, I will talk about how we solve these challenges. We first conduct an empirical study to understand the challenges of integrating machine learning cloud APIs into software and the consequences of the integration problems. We studied 55 Python applications where ML APIs are used to make control flow decisions. As shown in the table, they cover a wide range of machine learning tasks. For each application, we created 100 test cases to offer roughly even coverage for all the passes in the function that invoke the ML API. Test inputs are from various sources, search engine, YouTube, public datasets, and audios recorded by the participants. Among all the unit tests, around 16 of them failed. Almost all of them are non-fail stop failure. At the first glance, one might blame the ML service providers for high failure rate. However, for both vision and language applications, the majority of testing failures are actually not caused by the incorrect output. In total, 2/3 of the test failures are caused by the ML API outputs that are correct but do not match with the software's need. Our further study reveals 3 main types of mismatch. Here we use a property management application and example. So the first type is hierarchy mismatch. This is the most common type of mismatch, contributing to 1/3 of all the unit testing failures. We know that real-world entities hierarchical relationships. For example, one is subclass or a component of the other. One object can often be correctly described by multiple labels at different levels of hierarchy. However, a software application may only be coded to recognize one of these labels and causing this hierarchy mismatch. Here we show the example is about roof, lantern, and light. Besides it, there's also perspective mismatch. Given an object, we can output multiple correct labels that describe the object from different perspectives, like shape, texture, and colors. Perspective mismatches contribute to around 3% of all unit testing in our study. In this example, the software expects the API to describe equipment, while the API actually outputs its material. And the last type is focus mismatch. Sometimes the software application cares about a particular object in the input image or video, and yet the ML API outputs are about the other objects in the input. This contributes to around 1/4 of all unit testing failures in our study. In this example, the software expects the API to describe promptly, while the API thinks the hands are the main element of this image. ML APIs adopt statistical models without strict correctness guarantees. Therefore, from time to time, ML APIs produce incorrect outputs, which lead to about 1/3 of all the test failures. In the study applications, incorrect ML API outputs mainly come from 2 sources. First, the neural network volatility. A small perturbation of an input may trigger inner flows of the neural network models and lead to an incorrect answer. As another example, a real-time game tracker uses the text detection API to extract all the status logs from the screenshots. And here shows the logging area of 3 adjacent frames of a game video, which share the same text string at the same position. However, due to the minor background changes, the API recognizes different text from them and leading the software to make different decisions. And second, the low input quality. Sometimes the software input does not contain enough information for ML APIs to perform its cognitive task, like a blurry photo or a noisy audio clip. Here we illustrate a voice assistant application. It records the user's voice command and uses the recognized API to transcribe speech into text strings. It is supposed to play music when the user says, "play this sound." However, the ML API often wrongly recognizes as play sound, missing a character from the audio clips with a high speaking rate. This small mistake caused the software to misbehave, not playing the music when it should. So guided by our study, we propose SmartGear. SmartGear serves as a middle layer between ML APIs and software that uses them. It transparently and automatically checks and converts output of ML API calls, preventing ML API integration failures. To use it, application developers only need to apply a static code instrument routine to the applications, which inserts the SmartGL method after every ML API invocation. At the runtime for every ML API output, which is typically an array of values, SmartGL applies a series of incompatibility checking, starting from mismatch checking and followed by the incorrectness checking. Whenever SmartGL figures out a way to convert an output value, the new value is inserted to the original output array. So we conduct all the checking through the bytecode level instrument. Therefore, the developer's source code remains unchanged. At a high level, SmartGL tackles the mismatch between ML API output and software by examining the cognitive relationship between them. It includes several steps. First, for each invocation of an API, SmartGL conducts static analysis to obtain focal values to represent ML API outputs that software is interested in and knows how to handle. Next, at the runtime, right after the invocation of the ML API, SmartGL compares the API outputs produced there, which is typically an array of values with focal values associated with the ML API. The SmartGL's incompatibility detection checks if there exists any hierarchy, perspective, or focal mismatch, one by one. Guided by the empirical study, our checking is centered on using a knowledge graph to understand the cognitive relationship between the API outputs and focal values. So is the one the superclass or the alias of the other? Is the one from the different perspective of the other? Or is the one related to the other, even though there's no superclass relationship? And once a mismatch is detected, a conversion attempt follows. We'll first try to clustering the ML API outputs to software focal values, like clustering the roof lantern to the lights in the property management application. If it fails, we will try segment and ensemble strategy. So here's another example. When the ML API outputs furniture initially, the SmartGL would not immediately know how to convert this output, as the furniture is a superclass of both light and sink, which belong to two different focal value sets. So in this case, SmartGL will segment the photo into 4 pieces and try again. And this time it correctly recognizes there's sink in the image. Okay. As discussed earlier, it's difficult to automatically judge whether the output of an ML API is correct or not. SmartGL tackles this challenge by leveraging information beyond a single API invocation. First, validate across the APIs. SmartGL utilizes earlier invocation of other APIs on the same input. For example, a smart album uses Google's face detection API to find human faces in the image. It then invokes Google's label detection API to categorize the same image with the focal value face. While the former is a more specialized API for finding humans, the later API is also able to classify human images. Therefore, when one of them recognizes the face but the other does not, the SmartGL will regard the later as incorrect and adds face to the output array. Second, validation across inputs. SmartGL utilizes earlier invocation of the same API on the similar inputs. Let's go back to the flood depth application. The SmartGL detects the object localization API provides different vehicle detection results across the adjacent video frames. SmartGL then invokes the corresponding video API, which finds all the vehicles in the image, and forwards the last frame result to the software as a correction of the most recent invocation of the original vision API. And finally, validating across software and ML APIs. It will cluster ML API output to software focal values, particularly for those have text string outputs. And next, I'll introduce the evaluation. So we evaluate SmartGL using 65 applications, including the ones in our empirical study and also the additional ones. And we also design a new set of tasks for each application using the similar methodology. And we compare SmartGL with 4 baselines: crash only, which only captures the software crashes; ML API only examines the ML API confidence scores; software only examines the control flow of the software; and the last one, the software segment, it will apply the segment and ensemble strategy. In summary, our SmartGL detects 70% failures with neglectable false alarms. For the 300 incompatible ML API output missed by SmartGL, there are mainly 2 reasons. First, 60% of the false negatives are focus mismatches, which are not only common but also inherently difficult to detect. Second, over a third of these false negatives are incorrect API outputs. SmartGL fails to detect them as it assumes that ML API is reliable for most of the cases. In comparison, the four baselines either miss many failures or raise many false alarms. The ultimate goal of SmartGL is to improve applications execution correctness. So SmartGL achieves this goal by improving the average execution correctness rate across all applications from 84% to 95%. It resolves one-third incompatible outputs using all four types of fixing strategies. In comparison, the software segment, the other scheme that has failure prevention capability, is only able to eliminate 126 failures, improving the execution correctness by only 2%. And here is our ablation study. It shows that all of our components all contribute to our results. And finally, I will go to the summary. So the integration failure is widespread in machine learning software. To solve this problem, we propose SmartGL, a tool that automatically detects and converts mismatching or incorrect ML API output at runtime, serving as a middle layer between ML API and the software. Our evaluation proves its effectiveness. We welcome people to try our tool and join us in improving machine learning software. Thank you.
So thank you for that talk. So I'd like to invite people to come forward to the microphones to ask questions if they have any, and do introduce yourself for the remote audience. I can start us off with a question. So it seems like the APIs that you've been talking about in your talk are are either taking like image or video as input. Can you talk about what other techniques might be needed for, say, APIs that take a natural language input or like audio input?
Yeah, great questions. So I use the image ones just because it's easier for me to present in the slides. Actually, we study all the three types of applications. So let me just find the one we showed. Yeah, so we cover all these types of APIs. So they include the vision ones, the language ones, and also the speech ones. And these are the popular categories from the commercial cloud API services.
Any other questions from the audience? Okay, let's thank the speaker again.